Welcome to video 2 for this unit on two-variable statistics. In this video, we're going to focus on scatter plots. While working in math class, it can be easy to forget that reality is somewhat messy. Not all oranges weigh exactly the same amount, beans have different lengths, and even the same person running a race multiple times will probably have different finishing times. We can approximate these messy situations with more precise mathematical tools to better understand what is happening. We can also predict or estimate additional results as long as we continue to keep in mind that reality will vary a little bit from what our mathematical model predicts. For example, the data in this scatter plot represents the price of a package of broccoli and its weight. The data can be modeled by a line given by the equation y equals 0.46x plus 0.92. The data does not all fall on the line because there are many factors other than weight that go into the price, such as the quality of the broccoli, the region where the package is sold, and any discounts happening in the store. We can interpret the y-intercept of the line as the price for the package without any broccoli, which might include the cost of things like preparing the package and shipping costs for getting the vegetable to the store. In many situations, the data may not follow the same linear model farther away from the given data, especially as one variable gets close to zero. For this reason, the interpretation of the y-intercept should always be considered in context to determine if it is reasonable to make sense of the value in that way. We can also interpret the slope as the approximate increase in price of the package for the addition of 1 pound of broccoli to the package. The equation also allows us to predict additional values for the price of a package of broccoli for packages that have weights near the weights observed in the dataset. For example, even though the dataset does not include the price of a package that contains 1.7 pounds of broccoli, we can predict the price to be about $1.70 based on the equation of the line, since 0.46 times 1.7 plus 0.92 equals approximately 1.70. On the other hand, it does not make sense to predict the price of 1,000 pounds of broccoli with this data, because there may be many more factors that will influence the pricing of packages that far away from the data presented here. Some data appear to have a linear relationship, so finding an equation for a line that fits the data can help you understand the relationship between the variables. Other data may follow nonlinear trends or not have an apparent trend at all. When modeling data with a linear function seems useful, it is important to find a linear function that is close to the data. The line should have a y-intercept and a slope to follow the shape of the data in the scatter plot as much as possible. The interpretation of the y-intercept should always be considered in context to determine if it is reasonable to make sense of the value in that way. Technology can be used to quickly find a line of best fit for the data and provide the equation of the line that we can use to analyze the situation. When fitting a linear model to data, it can be useful to look at the residuals. Residuals are the difference between the y value for a point in a scatter plot and the value predicted by the linear model for that x value. The lengths of the dashed line in the figure are the residuals for each data point. For example, in the scatter plot showing the length of fish and the age of the fish, the residual for the fish who is 2 years old and 100 millimeters long is 8.06 millimeters, because that point is at 2, 100, and when x is 2, the linear function has the value 91.44, which is equal to the quantity 34.08 times 2 minus 23.78. The residual of 8.06 millimeters means that the actual fish is about 8 millimeters longer than the linear model estimates for a fish of that same age. Thank you for watching video number 2 of 3 for this unit on two-variable statistics.